Hello, and welcome to our session on DeMorgan's Theorem, one of the most important Boolean relationships that we'll use in the design of digital logic and circuits. DeMorgan's Theorem is a Boolean relationship or law that's particularly important because it allows us as digital circuit designers to take the inverse of any function easily and also to convert a logic function to a form that can be implemented using only NAND, only OR, only NOR, or only AND gates. NAND gates are particularly important because they are the smallest and the fastest of all logic gates. DeMorgan's theorem occurs in 3 different steps, which we'll explore here for 2 different problems. The first problem, we'll take an OR gate, a NOR gate, and convert it to an AND gate. And we do that in 3 different steps, starting with the NOR gate, A NOR B. The first step in DeMorgan's theorem will be to invert the function in its entirety, and that will give us a double inverse or double bar, which is effectively the same as A or B. The next step will invert individual variables, inverting A as well as B to get A naught or B naught. And the last step, to get an accurate but equivalent representation of A nor B, will be to convert the ORs to ANDs and the ANDs to ORs. In this case, we only have one OR, so we'll convert that to an AND. And that effectively gives us an AND gate when we started with a NOR gate. And that's shown here as starting with a NOR gate, which is equivalent to an AND gate with the same inputs inverted. We can also apply DeMorgan's theorem to a NAND gate. Going through the same steps, we'll first invert the entire function, A NAND B, and that double inversion will just give us A and B. The next step of DeMorgan's theorem will invert each individual variable, and the last step of DeMorgan's theorem will convert our ORs to ANDs and our ANDs to ORs. In this case, there's only one AND. We'll convert it to OR, and we'll have effectively converted a NAND gate to an OR gate. So DeMorgan's theorem can be used and applied to a variety of different gates to convert between them. It can also be used to convert the inverse, to compute the inverse of a function. Here in this example, we'll compute the inverse of a function called out, which is expressed as ABC or AB. The inverse of that function will just involve putting a bar over the entire function, and then we'll use DeMorgan's theorem to simplify it. So first we'll apply DeMorgan's theorem in 3 steps to the overall function. First we'll invert the whole function, which will put double bars over the function. Next we'll invert each individual variable, and the double bars here will go away because they cancel each other out. And finally we'll convert the OR to an AND, and that'll give us a separate but equivalent expression for the inverse of out. Now we can repeat this process to come up with an expression that can be simplified using other Boolean relationships. We can now apply DeMorgan's theorem to ABC naught and to AB naught. And when we do that, we'll get A naught or B naught or C naught ANDed with the DeMorgan's equivalent of AB naught, which is A naught or B naught. From here we can multiply everything out and simplify it. We'll get A naught or A naught B naught or A naught C naught or A naught B naught or B naught B naught or B naught C naught. Now there are quite a few things we can simplify here. Let's start by simplifying B naught and B naught and A naught and A naught. Any variable ANDed with itself is simply that variable, which gives us A naught or A naught B naught, or A naught C naught, or A naught B naught, or B naught, or B naught C naught. Now we can pull the A naught out of the expression here and get A naught times the quantity B naught or 1. And we can do the same thing over here, pulling B naught out of the expression times the quantity A naught or 1, or B naught C naught. Any variable ORed with a 1 gives us a 1, and then ANDed with a variable gives that variable. So this simplifies to A naught or A naught C naught, or B naught or B naught C naught. We can do the same thing once again to get A naught times the quantity 1 or C naught, or B naught times the quantity C naught or 1, which gives us finally A naught or B naught. And that is the inverse of our original function out. In this way, we've applied DeMorgan's theorem to simplify an expression that we started with here that wasn't possible to simplify using any other Boolean relationships. We can also use DeMorgan's theorem to replace gates from AND gates, NAND gates to OR gates, from AND gates to NOR gates, from NOR to AND, and finally we can also go from OR to NAND. Let's take a look at how this works in practice. Let's start out with our expression again, out equal ABC or AB. That requires 2 AND gates if we implement it without simplifying it. And then we'll take the outputs of those 2 AND gates and OR them together to get the output. Now using DeMorgan's theorem, we can fully implement this using only NAND gates by taking a look at the chart here to see that a NAND gate is equivalent to an OR gate with inverted inputs. So we'd like to convert this OR gate to a NAND gate. We'll do that first by inverting the inputs, but in order not to distort the accuracy of the output, we'll have to double invert. And now we have an expression and implementation that's identical to what we started with, but we see now that we have an OR gate with inverted inputs, which is simply a NAND gate, according to DeMorgan's theorem. In the process of double inverting, we also created 2 NAND gates at the input to our implementation. And so now we have the output implemented as a function of 3 NAND gates. We can do a similar thing to come up with an implementation that uses only NOR gates and inverters. In this expression, out starts as a function of OR gates. And without simplifying it, we'll just OR together A and B, then B or C, and then we'll invert B, and we'll AND those together to come up with the output out. Now to convert this to a NOR gate implementation, we can do something very similar to what we did with the NAND gate implementation, double inverting these intermediate signal lines, and then putting in a double inversion here along the B line. And now we have an AND gate with inverted inputs, which is equivalent to a NOR gate, and that'll get us to a fully NOR gate implementation. We'll NOR A and B together, and then B and C together. And finally, B is inverted twice, which is equivalent to just B. And in the second stage, we'll have a single NOR gate replace the AND gate with inverted inputs. So using DeMorgan's theorem, we've seen how we can convert any logic gate implementation to one that only uses NOR gates and inverters, or to one that only uses NAND gates and inverters. DeMorgan's theorem has also allowed us to take the inverse of any Boolean function, and we've looked at converting gates within an existing implementation to one with other gates that may be more space efficient or faster than the original gates. Well, that's all for DeMorgan's theorem today. Thanks so much for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.